So I'm Dan Schatzberg, and I'm talking about an operating system architecture for cloud computing. And this is joint work with my group at Boston University. And there's been a lot of innovation in cloud computing. I've shown here programming models like MapReduce and NoSQL databases have been pretty important, but also the way we build data centers and the way we manage them has changed pretty significantly. But in contrast, there's been relatively little innovation at the operating system level. Arguably, we have less diversity there than we did, say, 15 years ago. And so we asked the question, do operating systems even matter in the cloud? And I wouldn't be here if I didn't think that that was the case. Recent research shows, for Memcached, 90% of the time is being spent in the kernel. And this is pretty typical of a lot of different applications in cloud computing. So we wonder, how can we enable OS innovation in the cloud? And there's sort of these two typical approaches that are taken. And if we modify an existing operating system, we get to depend on this large software ecosystem, right? Not only do a lot of applications exist on our operating systems and are written to these interfaces, but we have device driver support. So any innovation in this context has a good chance of being practical. But that's also a disadvantage, right? These systems tend to be large and complex, and any innovation is constrained by that. You have to work with every other piece of the system and make sure that it all functions correctly. And the alternative approach is building a clean slate operating system, something completely new. And you get the benefit of complete control there. And that's great. We can solve the problems in any way we want, but on the flip side, we have to reproduce a lot of existing functionality. To be practical, you have to support existing applications and the interfaces they depend on. So these two approaches just aren't cutting it. They have serious roadblocks, and we haven't really been innovating much at the operating system level. So I'm here to present a way forward, an operating system architecture which enables further OS innovation. And our insight is this. Basically, look at a cloud application. I've shown here a typical web application. I've got a web server, I've got databases, I've got business logic, a caching layer, and what's the properties of this kind of an application? Well, it's first of all a distributed application. Historically, our operating systems come from this environment of a big server and lots of applications running on top of it. This is one application, many machines for it. And with infrastructure as a service, I can provision on demand. And just my Java portion of my application, I'll provision resources for it and run more Java instances if I need. And another property here is that I have this isolation. Usually it's done through virtualization, but my application is on its own set of machines. I can even have a private network back here connecting everything. Again, that's usually through virtualization, but that's increasingly important and also done with bare metal provisioning and whatnot. And so we look at this. This is a really different environment from where a system like Linux comes out of. And we ask, well, what's the role of the operating system here? What is it actually serving? And for one, our operating system doesn't need to support multiple users. Certainly it doesn't because we're dedicating the machines here, but it doesn't even need to support multiple applications. We're dedicating it for a single purpose here. And what's its role to play with resource usage? Usually in operating system, it's an important aspect to make sure that all the competing processes are getting a fair share of the resource, but again, we typically run one thing here. And a third point is that we also don't need this homogeneous mixture of operating systems all serving the same purpose. Certainly our application doesn't look that way, right? We have a database somewhere, a web server somewhere else. Why should our operating system be identical everywhere? And so that leads us to this approach, which is, we can take this and just customize an operating system for one portion of our application. I'm going to deploy memcached, not with Linux, but a custom operating system. And in fact, I can take this kind of old approach called library operating systems, where because the operating system is only deploying memcached, it can be linked directly into the application address space. And that means it can run ring 0, no protection necessary, and whatever is in there can be customized for specifically that purpose, whatever memcached needs. And we can in fact take this approach also, run Java with its own operating system, and that's a pretty well-studied area in the literature. People have pointed out that giving access to page tables is a pretty big deal for garbage collection. And it can do this with all of them, right? They can all run a custom operating system. And it's great, except I've sort of made this impossible. I'm going to deploy my application with 4 different operating systems, and yeah, maybe they'll be customized for each of these pieces of the application, but what about logging, configuration, management, tooling, all these things that are common to the system, they're each going to have to solve in their own separate way. But there's actually something we can do to mitigate this a little bit. We argue that you should actually keep some of your general purpose operating systems here. There's a lot of value. For one, you can just offload any non-performance critical functionality from these custom systems to our general purpose operating system. So rather than memcached needing to find a way to provide a logging service, it can be offloaded to our Linux machine running Apache. And we can log there and check the logs there and manage the application. The more general point is this isn't just a bunch of loosely coupled systems, it is a single system, and they should work together to provide some common service. And so we call this architecture the Multilibos. And I want to give a precise definition that a Multilibos is a tightly integrated composition of general purpose operating systems and specialized library operating systems. And the key point is that they're tightly integrated. They're not each serving an individual purpose, but rather part of a whole. And I'm maybe a bit vague here with the term integration, but you can think of different mechanisms you can do there, right? A few examples: you can build on distributed shared memory, or maybe use message passing. A system called Plan 9 used distributed file system as a mechanism for integrating different pieces of the system. But whatever technique you use, the value you get out of it is that there's this trade-off you can make between how much effort you're willing to expend and what utility you get out of it. And the word utility, maybe you think of it as performance, but there's other aspects you can get out of it. You can build an elastic system. Maybe you care about the power consumption of your system. So when we look at how can I deploy an application in the cloud, I get to decide how much effort is it going to take me and what's the utility I get out of that. And if I just use our existing general purpose systems, it's great. It's not high effort, but it's also not the highest utility I can get. Our operating systems, just by the nature of being general, limit us a little bit. And on the other end of the spectrum, we can make custom special purpose systems, but as I discussed, it's a lot of work. You've got to build a lot of functionality. So this architecture, the Multilibos, really lives in this space between, and you can choose. I'm not going to build a custom special purpose system for everything. I'm just going to take a piece of the application and deploy it that way. And so you can move in this space between and make progress. So I want to be concrete here with a couple examples. Take our web application and just replace memcached with its own library operating system. And what does that buy us, really? You can look at memcached on Linux. There's this process of an interrupt, a network device driver, network processing, and then finally get to memcached. And this is really only half of it. Normally memcached also sends a reply out. But there's a lot of inefficiencies in the way that this is actually done. For one, every time you have an interaction here, there's some scheduling going on. You have to do a context switch to user space, which is just how the system works. That's separation of protection necessary. And also for this period of time, I have interrupts enabled. And anytime a timer fires or another device needs some interaction with the system, it's going to interrupt the processing. I'll pollute my cache a little bit. And of course, that's how I would expect a general purpose system to work. I want it to be responsive to scheduling and to enable multiple applications to process. But here it's really not that necessary. I'm only running memcached on these machines. Additionally, I have to copy a packet to user space. Primarily that's because of protection. I'm DMAing memory from the device into kernel memory. And to get to user level, I usually need to do a copy. Another point here, the network processing is doing a lot of validation, protecting from denial of service, which I would expect my laptop running to also do that. I need to protect from outside sources, but in the way I describe this application, it's not necessary. It's in a private network, and I'm only accessing it from my own software. So, a library operating system can take an approach that looks a little different. I mean, it's the same general process, but these can be combined with just function calls. I'll link it all into the same address space, run it ring 0, and I'll have interrupts disabled the entire time. I don't need to be concerned about scheduling other things or responsiveness because I know memcached is the only thing running. It's already an event-driven application. And so I'll only enable interrupts when I'm done a full request. Additionally, I can support zero-copy interfaces and any number of further optimizations, right? I don't really need virtual memory here or paging because memcached is keeping everything in memory, and I don't need any complex scheduling here, just an interrupt dispatch loop. Additionally, I have a pretty small system image, so when I'm not constrained by needing to support everything in all these applications, I can do some pretty radical things at the system level and still depend on the logging that I get out of a general purpose system. And that offload is really important, that I still have other systems that I can depend on to provide this full functionality. But I can also offload in a different direction, right? I can offload performance critical functionality from a general purpose system to a specialized system. And that's the point of this next example. Take this application, it's called Sage. It's an open source interactive mathematics environment. So if you're familiar with MATLAB or Mathematica, it's similar to that. It's written largely in Python, and it's huge. It's got a ton of libraries that it incorporates with. And in the cloud, I might deploy it on Linux and let users log into it and do their work on it. And this is great until a user tries to create this huge matrix, 1,000,000 by 1,000,000 elements. Sage is going to complain, I'm out of memory, I can't support that. And what this architecture lets us do is, if someone does that, maybe we spin up a bunch of machines running custom system just for mathematics or just for doing a matrix operation. Rather than having to support this whole rich Python Sage environment, we just take a portion of the application and distribute it. And if we do this, the systems that we build for the performance critical aspect here, we can focus on things like how we do the I/O between them, elasticity, scalability, and it gives us a lot of utility to separate out the functionality in this application. And I also want to talk, nearing the end here, a little bit about the challenges in deploying such a system. you inevitably want to find the reusable pieces of OS functionality. That the way I deploy memcached and the way I deploy my web server, there's some similarities there. I'll find what's reusable. But when you do that, it's oftentimes in a tension between how much can I make this reusable and how much can I actually specialize this for the particular application I'm working on. And another point here, I've called it versionitis, that I'm advocating for this great diversity in operating systems. I'm going to see customizations for all these different applications, but it comes with all these known problems that how I configure different versions of operating systems and how they interact with each other is really a challenge to overcome. There's some hope that this is also a problem at user level, and yet we still make software, but it's not clear that the same techniques can apply. And this third point I've made is that you want to avoid building a new operating system. It's this tendency to, okay, I'm going to build this component and that component, and we're going to get this vertical stack of software where our applications can be written to. But if they're too tightly integrated, you're back at the same point you started out, and you can't specialize them at all. And I want to end on this point. We're working on a system called the Elastic Building Block Runtime, or EPRT. And you can think of it as a Multilibos toolkit. And we're very particularly interested in elastic applications. And so there's a collection of components that we hope are efficient, reusable, and customizable for building these different applications. We have some preliminary results. I'm not going to go into too much here. We deployed memcached in a similar way to how I described earlier. And at our peak, we get almost 2 times the throughput of memcached running directly on Linux. So there's a lot of opportunity here to do better than our current operating systems. And when you really are unconstrained by building general purpose systems, you can take advantage of this. And I'll be happy to take any questions. If you want to check out our website, you can see there, or email any of us.
Sure. Gino Wang from the IBM Research. So very nice talk. I see the trend like a network virtualization, all these things happen in the hardware side as well. So hardware actually gives functions to the application directly, then they bypass this operating system and they just DMA the package to the user space directly. All these, the hardware virtualization actually enables all these, operating system avoidance between, right? And your work is actually modifying this operating system and add more functions on the, on it, and made it possible to do it. So, do you have any intuition if you apply your scheme to the virtualized, platforms, so how it's going to work and what it will look like in terms of like this virtualization? I mean, compared to the hardware virtualization and operating system virtualization.
Yes. So. I think it's a great match because we're really dependent on the fact that the infrastructure provider is isolating everything, and with hardware virtualization it only gets better, right? You can we have a dedicated NIC. We don't have to take VM exits to interact with it, and deploying a custom operating system on top of it makes a lot of sense. And there's, as you point out, this trend towards virtualizing all the hardware, not just the CPU. Mm-hmm. And that means that we can do a lot of interesting things with how we manage our devices.
Mm-hmm. Okay, thanks.
Hi, Steve Muir from Comcast again. I'm willing to be preempted or interrupted by anybody who's everyone's higher priority than me. I've used up all my credits, right? So people have been talking about this stuff for 20 years, right? Exokernels, and no one's been really successful at scale. And it kind of made me go right back to your first slide where you said, look, 90% of the time is spent in the kernel, so obviously it's worth looking at. But maybe if there's a lower bound, which is 89% of the time, it's just what it would take to move the stuff around in the best possible case. Maybe it's not worth looking at, right? And Mike Franklin kind of alluded to that. He's kind of like, we've got all this other stuff that we gain by just not worrying about operating systems and languages, just by doing Java, right? And so the question is, have you established that there's enough headroom underneath that 85%? You said 85 to 95%, right? Is there actually enough things where, if you could say, I know I can get it down to 10%, right? Not in terms of percentage, but in terms of number of cycles, right? Can you reduce the absolute number of cycles required on today's hardware to move the stuff around significantly enough to make this all worthwhile? Or at some point, and I think that's why it hasn't worked, right? Because things have got faster and faster, and everyone said, you know what, I just don't care. For all the complexity that this brings in, I'll just pay the penalty, and my life will be easy, and let's just move on and talk about Java.
So I'll answer that in a few different ways. So one is our preliminary results at least give us some indication that there is a pretty big gap between what's possible and what our current systems do. Another thing is there's more than just performance here. I want to deploy a cloud application on top of a general purpose system, and it's the only thing I'm running. What's the first thing I do? Well, I spin up, create all my threads, and I'll make sure they're pinned to all the cores. And I'll make very careful that the memory I use is pinned correctly, or I'm mapping at the right page size. And the point I'm making is that the interfaces that our general purpose systems already provide give us a lot of hard time, right? I have to do all this thing to make it deploy a single application as well as I can. And a custom system can say, no, that's actually default. That's how you write your applications. So, I showed here our memcached results. Memcached for us was less than 300 lines of code. And that's just because that's the system. It was built for that kind of purpose, and when you want an event-driven application, that's what you get. And so there's more wins than just performance, but also I can deploy managed code environments, and for some people, you're a smart guy, you're going to figure out, I'm going to deploy the JVM in this great way, and then everyone's Java application just runs better for free. I think one of the reasons it hasn't been successful is partially because we've tried to do the same things that haven't been successful for so long. And there's this tremendous opportunity in cloud computing to do much better.
So I think you might be on something with the Java virtual machine, right? Where for many applications in enterprise, that is the platform. I think once you start getting to smaller components, you run into sort of exponential growth of how many of these things I need, right? And that's what's killed this in the past, is it's kind of like, yes, I can build a memcached, and you could build a DNS, and I could, load whatever, but once I try to jam them all together, well, we have like incompatibility hell. So I mean, this is cool stuff. I like it. I think it's very encouraging. I think something like a targeted, bare metal JVM, which again, people have already tried that, but maybe that's, I do think there's some interesting paths here. This is good stuff.
Thanks.
Have you looked into the RamCloud project at all? And they seem to have a similar notion around latency, but it's not boil the ocean kind of a change.
Sorry, which project?
RamCloud.
RamCloud, yeah. My familiarity with them is not as necessarily in a separate OS architecture, but this notion of building not only custom software, but custom hardware also for special purpose. And I think definitely it's along the same lines of what we're arguing for here, is that we can really strip away a lot of the layers to do some efficient things like in-memory storage that they're doing.